This video contains the solutions for exercise set B from the Taylor series questions. Number one, we are supposed to find the first four non-zero terms and the general term of the Maclaurin series for the g of x function, which is the antiderivative of sine of x squared with an initial condition g of 0 equals 1. That's telling us what the c is. So don't forget about this and give its interval of convergence. That's part A. All right. So the first thing we should do is find the series for x squared, for sine of x squared, excuse me. That's part A of number 1. I'm going to go ahead and just write that down because we've seen this enough. We're just plugging in x squared into the sine function, and that is going to double all of those powers. Excuse me for 1 second. Sorry about that. And that's x to the 14th over 7 factorial and so on. And now we want the antiderivative of that with initial condition g of 0 equal to 1. All right, the antiderivative of x squared is x cubed over 3. Antiderivative of that is x to the 7th over 7. Antiderivative of that is x to the 11th over 11. 5 factorial. And then how many terms do we want? The first four non-zero terms, so that's x to the 15th over 15 times 7 factorial. And the general term. But we have g of 0 equals 1, so when I plug 0 into this, I get 0, 0, 0, so I want to have a 1 out here at the front. Okay? Now, a question was asked to me, how do you write the general term when there's this 1 here? We just write first term is 1, and then all other terms, well, we'll call this, I don't know, I guess you could call this the first of the other terms. I'm going to make this the second term. That makes more sense to me to call that the second one. So here we go. See if we can do this. I want the top. The top is numbers that are going up by 4, right? They're going up by, they're odd, but they're every other odd. So that means I have to have x to the 4n, and then if I'm starting at n equals 2, then when I plug 2 into this, I get 8, right? And I really only want 5 there, so I'm going to have to do 8 minus, I really only want 3 there, I mean. So 8 minus 5. So if I plug 2 in there, I get the right first number there. And then on the bottom, I have that same number keeps showing up, so that's 4n minus 5. And then this number, these are just odd numbers, and odd numbers are of the form 2n. If I start with 2, I want the first factorial here, that's like times 1 factorial, right? 1, 3, and so on. If I plug 2 in here, I think I need that to be 2n minus 3, right? So if I plug 2 in there, I get 4 minus, I want the first one to be just 1. So that's pretty crazy looking. And times negative 1 to the, if I start with 2, that's going to give me an even, so that's going to work right there. So that's pretty crazy. If you did that starting with like 0 or 1 instead, that's fine. I wouldn't worry about that. This is a pretty crazy one. You're not likely to see one as complicated as that on the AP test. B. Use the series in part A to find the first four non-zero terms in the general term of the Maclaurin series for the antiderivative of x times this series. Alright, so I'm going to multiply all these by x. That gives me x plus x to the 4th over 3 minus x to the 8th over 7 times 3 factorial plus x to the 11th over 11, sorry, x to the 12th, multiplying everything by x, right, times 5 factorial. And then I want to find the antiderivative of that, and this time the initial condition is 0. So what's the antiderivative of this? The antiderivative of x is x squared over 2 plus x to the 5th over 3 times 5. I'm not going to multiply those out because it's going to be easier to write the general term if we can see what is going on here. So that's going to be 7 times 9 times 3 factorial, right? Those were already there, and I divide by the new exponent, plus x to the 13th. It's 11 times 13 times 5 factorial. And then my c at the beginning, that's just 0. So again, you have to treat these as separately. The first term came from sort of somewhere else, didn't come from the same recipe. The first term is x squared over 2. And then the rest of the terms, we'll call this the second term. Let's see. I have x to the, these are going up by 4s again, so that's 4n, and then if I plug 2 into that, this time 4n minus 3 is going to get the job done, over, if this is the second term, it looks like I have a couple of odd numbers here. This particular sequence of numbers goes 3, 7, 11, so those are going up by 4. That's 4n. If I plug 2 in here, that gives me 8, and I want that to be 3, so that'd be 4n minus 5. And then I'm multiplying by another number that's 2 bigger than that, so that'd be 4n minus 3. That takes care of those two numbers in each part of the pattern. You can see if I go to here, that'd be the fourth term. That'd give me 16 minus 5 is 11. And then if I plug in 16 minus 3, that's the 13, right? So that's working. And then I have the odd factorials, 1, 3, 5. So that's 2n. If I plug in a 2 into this, I'm supposed to just get 1 factorial, so that'd be minus 3 factorial, and it's alternating, oops, negative 1 to the n. And n, since the first term's even and positive, that works. Those are really crazy general terms, and pretty crazy stuff here. If you can make your way through that, you're in great shape. Number 2. Find the first 4 terms in the general term of the Maclaurin series for the derivative of x squared over 2 minus x squared. We're supposed to find the series for this first and then take the derivative. So let's find that series. This looks geometric. I need to factor out a 2 off the bottom. That's going to look like 1/2 x squared over 1 minus x squared over 2. When I factor the 2 off the bottom, you can check to see that if you multiplied that by 2 over 2, you would get the same thing as that. And that series is going to look like the first term is 1, or x squared over 2, I guess we could write it as, x squared over 2. And then my multiplier is x squared over 2, positive. That's x squared, x to the 4th over 2 squared plus x to the 6th over 2 cubed, and so on. That's the first 4 terms. And then we want the derivative of that. So what's the derivative of x squared over 2? It's x. The derivative of this is, let's see, the 4 cancels that. I'm going to say it's 4x over 2 squared. Are they asking for a general term here? They're not. So that means I can simplify. I don't need to find the pattern, so sorry. Then I'm going to simplify. That's 2 squared is 4, so that gives me x cubed, right? That's x to the 4th over 4. Derivative of that is x cubed. This is x to the 6th over 8. So the derivative of that is 6/8 x to the 5th. And then this is 8 over 16, so that'd be 1/2 x to the 7th. You see when you reduce, it's kind of hard to see what the pattern is if we needed a general term, but we don't. Oh, we do need a general term. Dang it. All right, so hoop. So let's see. Let me rewrite these unsimplified. So that would be 4x cubed over 2 squared plus, this is 6x to the 5th over 2 cubed. That would be 8x to the 7th over 2 to the 4th, and this is x squared over 2. So let's see what's going on here. The nth term is, oh sorry, that's just x to the 1st over 2. The nth term would be the powers of x are odd numbers. So let's say 2n plus 1. And as soon as I write that down, that means I'm starting at n equals 0, right? And then on the bottom, I have 2 to the 1, 2, 3, 4. But since I started at 0, that's 2 to the n plus 1 power, right? Because this is the 0th term. And then on the top, I have numbers. Oh, this was 2, sorry. This was 2x over 2, and those canceled out here. So I was looking back at that term. So those had canceled out. But better to see this is now 2, 4, 6, 8. So those are even numbers, which are 2n plus 2, right? Because if I start here with n equals 0, that would give me 0, and I want the first one to be 2. So they don't alternate. That's the general term. The interval of convergence. Let's see if we can do that. Let's do the ratio test real quick. So what's the limit as n approaches infinity of the n plus 1 term? So let's see, that's x to the, when you plug n plus 1 in here, you're doubling the n and the 1, so that's 2n plus 3 times, when you plug in n plus 1 here, again you're doubling the n and you're doubling the 1, so it's going to be 2n plus 4 over 2 to the n plus 2, right? When you make this n plus 1, it's not getting multiplied by anything, so just get one extra one there. Times this upside down. Alright, let's simplify what we can here. Looks like I've got one extra 2 on the bottom. I've got 2 extra x's on the top. I'm going to leave x squared on the top. And that is not part of the limit, so that can come to the outside. Times the limit as n approaches infinity of 2n plus 4 over 2n plus 2. That limit is 1. It's just equal to x squared. That means x squared has to be in between -1 and 1, which is the same as saying that x is between 1 and 1. We should check the endpoints. If I plug in 1 into this, what do we get? Plug 1 into, I guess we should probably plug it into this version so we can kind of see what's happening. It looks like we are getting, let's see, that would be 2 over 2 plus 4 over 4 plus, we're just going to get the coefficients, 6 over 8. Is that going to converge? Let's see. The bottom numbers are a p-series, right? No, they're not. Sorry. The bottom is a geometric series. That's what I meant to say. Bottom we're multiplying by 2. That's geometric. And on the top, those are getting bigger. Whew. I'm not sure right off the top of my head. Let's see. So the terms are going to 0, but they're not alternating. And they're not going to alternate when we plug in -1 either, because it's just going to give us the negative of all those. So I think that they're both not going to converge. Let me just check something real quick. Hold on. Let's see. I'm looking in my little solutions packet. Let's see. My instinct says that it does not converge for those. Uh-oh. It looks like I have the wrong interval of convergence, too. They have it converging from -square root of 2 to square root of 2. So what did I do there? It looks like I have the right terms. They have that. Hold on, they don't have that. Oh, they have this. Yeah, they have the same general term as me, but they give a different And they don't say anything about that. So why did they get... Oh, because we forgot about the extra 2, didn't we? There's an extra 2 down here. That's why, right? We left that 2 out. And that's going to mean x squared when I multiply. If that limit is 1/2, that's x squared over 2, right? And that's when I multiply. That is indeed going to give me that. Okay, now let's see if that makes a difference for what our endpoints look like. When I plug in the square root of 2 here, I get 2 times the square root of 2 over 2. I get the square root of 2 as the first term. And then here I get 4 times the square root of 2 cubed is 4 on the square root of 2. No, it's not. It's 2 on the square root of 2, right? And 2 squared plus 6 times 5 square roots of 2. Some of them are going to, 2 pairs of them are going to pair up to be a 4, and then there's an extra one like that over 2 cubed. And it looks like what's happening here is these are all even. Now let me do one more. So that's going to be 8 times the square root of 2. If you have 7 square roots of 2, 3 pairs of them make 2's, and then there's one left over, so that's going to be 8 on the square root of 2. 2 to the 4th. So it looks like we're getting powers of 2 here. This is 2 to the 1st. This is 2 squared. This is 2 cubed. And then, since these are even numbers, there's always going to be a 2 left there. So this is going to cancel out with stuff on the top, and we're going to get an endless string of square roots of 2 that is definitely going to diverge. And when I plug in negative, it's just going to be all negative terms. So that is the interval of convergence. That was a little crazy. It's 17.5 minutes, and we're only done number 2. All right. Number 3. But I'm going to put these all in one video if it kills us. Let's see. Use the Maclaurin series for e to the negative x squared to approximate the integral 0 to 1 underneath e to the negative x squared. And they want an estimate for the amount of error there could be in our approximation. So the series for e to the negative x squared is the series for e to the x, but with negative x squared plugged in everywhere. And I'm just going to go that far. Oh, let's go one more. Oops, that's 3 factorial there. And that should be 4 factorial. Okay, and they want us to approximate what is the integral from 0 to 1 under this series. It's 1 minus x squared plus x to the 4th. And we'll use this many terms. It would be dot, 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 but they're asking for an approximation, so we have to stop somewhere. I'm going to go ahead and stop after 5 terms. So the antiderivative of this is x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial minus x to the 7th over 7 times 3 factorial. And I'll tell you what, let's do this. I'll use that for my approximation, and I'll save that. The antiderivative of my next term would be x to the 9th over 9 minus 9 times 4 factorial. Right? Now when you go from 0 to 1, the zeros just make them all 0. So really what we're looking at is this series with a 1 plugged in. That's 1 minus 1/3 plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial. And then although I'm not going to use it, the next term would be 1 over 9 times 4 factorial. So here's my approximation, and here is the error. So let's see if looks like they did a different number of them, maybe. So I'll do my own work here, and we'll see what we get. So 1 minus 1/3 plus, that's 1/10, right? The 2 is just 2 factorial is just 2, so 1/10 minus 7 times 6, that'd be 1/42. That gives me 0.743, rounded to 3 College Board decimal places. And then my error is less than the next term, which is 1/9 times 4 factorial is 24. So my error is less than 0.005. Hey, that means it's accurate to 2 decimal places. So whatever that adds up to, it's accurate to here, right? Cool. Number 4. We have a function defined by f of x is equal to 1/3 plus 2x over 3 squared plus 3x squared over 3 cubed plus etc., and they gave us general term there. They want the first 3 non-zero terms in the general term for an infinite series representing the integral from 0 to 1 of that integral. And they want us to use the series to find that integral. So let's see. From 0 to 1 of this series, 1/3 plus 2x over 3 squared, 3x squared over 3 cubed, etc. dx. So the antiderivative of 1/3 is 1/3 x, or x over 3. The antiderivative of this would be, we bump this up 1 to x squared and divide by the new exponent, so that's going to cancel that 2 out. Give me that plus the antiderivative of 3x squared is x cubed over 3. And you can see what's happening here. This is actually a geometric series with first term x over 3 and multiplier x over 3. ... So when we go from 0 to 1, of course the 0 just knocks everything out. So when we plug the 1 in, we're looking at 1/3 plus 1/9 plus 1/27, and so on. And that sum is first term over 1 minus the multiplier, and that's 1/3 over 2/3, which is 1/2. Sorry, went off the page. There it is, 1/2. All right, cool. Turned into a geometric series. Number 5, which actually you could kind of expect that if they said use the series to actually find the whole thing, it's got to be geometric, right? Well, I guess it's not entirely true. Maybe you could recognize it as something else, but it's got to be geometric or something else we definitely recognize. Number 5, function f has derivatives of all orders with this one looks familiar. Looks like the same numbers that we had in number 5 from yesterday, or number 6 or something like that. So here's your derivatives. -3. Remember this one? The third derivative is 4. So let's go ahead and write the series for f first. Just build it up from scratch. That'd be 5 minus 3x plus x squared over 2 factorial plus 4x cubed over 3 factorial, which is 6. So we can simplify that. That's 5 minus 3x plus x squared over 2 plus 2/3 x cubed. That's definitely the same one. I remember that. Write the third degree polynomial about a, so that's just about a equals 0. That just means it's Maclaurin. For h of x, the integral from 0 to x of this. So we're trying to find that. Okay, so antiderivative here is that's 5x, and we're actually using the x's for two different things here. If that doesn't confuse you, then it's probably okay, but probably we really should use t's on the inside here until we plug the x in. So I'm going to go ahead and do that. Instead, I'm just going to change everywhere where I would have written an x, I'm going to write a t, so I don't have them playing two different roles. That's 3x squared, t over 2 plus t cubed over 6 plus, let's see, I'm going to divide by 4, so that's 1/6, or t to the 4th over 6. You can check my terms there, but I think that's right. And then we're doing that from 0 to x. The 0 just knocks everything out, so it looks like this just with x's plugged in. All right, 5x minus 3x squared over 2 plus x cubed over 6 plus x to the 4th over 6. And let me just check that, make sure it's right, and then we're done. Oh, did they only want the third degree? Right, the third degree. Whoops, that's the 4th degree. Just kidding. That. We were talking about the tornado drill the other day, and how would you, like, in texting format, in the language of young people, try to get across the idea. Because it was on the radio and the news, all this tornado drill, and some people apparently thought it was really a tornado. And we came up with the idea that the best way to get it across in text message format, that it was really just a drill, would be tornado. JK. I don't know what made me think, oh, I guess I drew a little tornado on this. So there you go. There's 1 through 5, exercise B.